welcome to this episode of our podcast series, Sound of Finance. Today, we will be talking about quantum computing and its impact on the financial services industry. I'm Stefan Berens, mathematician and consultant at zeb. I'm joined today by two very lovely people. First, Marta Estarellas, who is a senior quantum engineer at Qilimanjaro Quantum Tech, which is a Barcelona-based quantum computing startup. Welcome, Marta. Thanks for joining us today and taking the time to sit down with us to talk about this really exciting topic.
Thank you, Stefan. I'm very happy to be here at the Sound of Finance.
Perfect. Second, my co-host, Matthias Lehneis, who is a computer scientist and senior manager at zeb. Welcome, Matthias. Thanks for joining me.
Hello, Stefan. It's a quite nice opportunity for me, and I'm very happy to be here with you to discuss quantum computing, as it's a topic that we are already covering in our working group Advanced Intelligence, because it will be one of the future trends and will majorly impact how we do IT in banks. So I'm very excited.
All right. Let's start then with a little bit of background for everybody before we go into the deep analysis. So what is quantum computing and what separates a quantum computer from a classical one?
So quantum computers arise as a new way of doing computation based on the laws of quantum mechanics. The formulation of quantum mechanics in the early decades of the 20th century not only has allowed us to better explain nature, namely what happens at very microscopic scales, but also had an impact into many fields, and computer science was not an exception. So that's the main difference between classical computers and quantum computers, the underlying physical paradigm that rules what's going on in the very microscopic scales of the device. So instead of having the bits as a basic unit of information, as we have it with conventional computers, with quantum computers we have what is called qubits, quantum bits. And they can be part of what are called superpositions or entangled states. These are very important concepts, as they are the two key quantum features that can be harnessed to do computation in a much, much faster and efficient way. And this is precisely what makes quantum computers so interesting, that we can make computations in a faster and more efficient way.
And can those computers do different computations or new computations that classical computers couldn't do? Or is it just a faster way of solving the same problems that we have solved the last 50 years?
Yeah, that's a very good question. So there are many practical problems in many areas like logistics, chemistry, drug design, materials that are very much limited by the computational capabilities of our computers. So even if we have supercomputers, we have parallel computing paradigms and so on, we can still not solve them. So it would take us an unreasonable amount of time to be able to tackle these problems, or maybe we don't even have an algorithm capable of tackling these problems. But quantum computers have the potential to lift many of these limitations and actually give solution to some of these currently untractable problems.
It sounds exciting. But will I, as a classical programmer, be able to use those computers, or do I have to learn new things to use those new types of quantum computers? Do you have experience already with this, or is it too new to say?
So we are now at the moment that we are trying to ask ourselves this question. So this is definitely a challenge. So we need to find ways to democratize quantum computing in such a way that this is not only for specialized people, and everybody is able to use it and exploit it. So for that, we need to understand how a quantum algorithm works, and we need to find, training programs and do some kind of education to the widespread community of computer scientists and computer experts to understand how they can take the most of this new type of computer.
And is there already some experience how you can use this for financial services? I know you already did some research and work on it. So what's the experience from this?
Yeah, we think financial services can be very much benefit by quantum computers. The reason for that is that many problems common in finance, such as portfolio optimization, credit scoring, fraud detections, are computationally heavy to solve. But at the same time, they require quick responses. So we need to be able to solve them in a very, very efficient and fast manner, because the financial market is evolving very fast and we want to maximize the profit and get solutions as quickly as possible. These problems can be casted as optimization problems to try to reach an objective. For instance, you want to maximize return and minimize risk when finding the best asset distribution. At this moment, these type of problems are tackled by complex statistical models that evaluate the different potential outcomes, and that's what takes a lot of time. However, those methods rely on algorithms that we call heuristics, and that they are not only they are not very fast, but sometimes they don't even provide the most accurate solution. So they rely on approximations. And this is a problem because, as I said before, we would like to perform predictions over large amounts of data as quickly as possible. So these new quantum solutions can actually be very good to tackle optimization tasks, such as the ones I mentioned before. And that provides a potential advantage of quantum computation for these specific problems.
Okay, so you mentioned a variety of topics that are interesting for financial services institutions. And now the question, of course, comes, when do we see that actually having an impact on the industry? When do we see this already applied to the market and the institutes?
Yeah, this is a very difficult question to answer because the truth is that the technology is not ready yet for what we call universal quantum computers. A universal quantum computer is a quantum computer capable to solve any problem, any quantum problem. And for this computer to exist, we need what is called fault tolerance. So we need to make these computers very robust against errors. However, this is very demanding in terms of technology, and the technology is not there yet. Nevertheless, we already have some small-scale prototypes, and actually we have a quite diverse set of them. And these are called NISQ devices. NISQ stands for Noisy Intermediate Scale Quantum Devices, and the main difference is that they are noisy, so we cannot really correct the errors, and the quantum information is very, very sensitive to errors. But for certain applications, we can start taking some advantage of them. So, for instance, many know how Google performed this very famous experiment in 2019 that is called Quantum Supremacy Experiment. And they were capable of showing how their device, their NISQ device, was able to outperform classical machines on an artificial application. So the question now is, how long do we need to start, instead of outperforming classical machines for artificial applications, start outperforming classical machines for practical applications for the industry? And the expectation is that very soon we're going to start being able to use these small devices for dedicated problems that will accelerate the solution in front of classical machines.
Interesting. You were just talking of or you mentioned that you're working on a type of quantum computer. Is there already some kind of dominant type or dominant architecture for quantum computers, or is there still a competition in the market? Which architecture will win?
There is not yet a definite hardware approach. So there's no dominant quantum computer architecture. There are many candidates and they are very, very good. So some of them perform very good for certain applications and some of them have very good resilience to noise and some of them are able to construct many qubits together, namely the superconducting qubits, ion traps, neutral atoms. But also there are many different approaches to do quantum computation. One of the most common ones is the one that is called gate model. This relies on the application of quantum gates, quantum logic to a quantum state. And the other one that is also very common is the adiabatic quantum computing model that is more similar to an analog way of doing computation.
So you described that there is essentially still a lot of areas where it's unclear which direction it's going, multiple architectures. Now, you work for Qilimanjaro Quantum Tech, who consults financial services institutes with respect to quantum computing. In the light of this still uncertainty and time frame, so what does that entail? What do you work on?
Yeah, Kilimanjaro is a full stack quantum computing company. So that means that we do hardware, we develop a quantum computer. We focus on the idea of developing coherent quantum annealers. So this is a different computing paradigm than the gate-based model. This relies on the adiabatic model of computation I mentioned before. And we do this with superconducting qubits. And on the other side, we also have a software team, a big software team that provides the access to this computing platform and also designs the algorithms. The goal of the company is, at the end of the day, to make our clients quantum ready. We are interested to work with clients, understand the problems, use cases, and fit the hardware design and the quantum algorithms with the information from our clients. So we call this our co-design approach. On top of that, as you mentioned, we also provide consultancy services to logistics, financial, and other institutions as well that start becoming interested in how quantum computing can help their business.
Okay, so given that if I were a decision maker in the financial industry, what are the implications of these developments, and what are, for example, developments I have to look or should look out for in the future?
Yeah, so I think one important tip to keep in mind for these decision makers is to be ready for when hardware is ready. So what do I mean by this is that it is important that early movers focus on quantum algorithm consultancy service. So this is allowing your company to start casting their problems into quantum one. So even if we still don't have a winning hardware architecture, we can already have our algorithms prepared to be run on a quantum device once this winner is already there. So in that sense, I think the time to start getting ready is now. This is a very competitive market, and many have already started to make a move. There are many large financial institutions. I know BBVA in Spain, JP Morgan, Citigroup, that are partnering with quantum computing startups and forming a small research teams to start doing what I just mentioned, to start becoming quantum ready and see how they can harness this new technology for their benefit. So now what to look for in terms of technology readiness. So what will say that a milestone has been overcome and we have quantum computing ready. So it's very common to look at the number of qubits. So that is a very technology readiness indicator that we see very commonly everywhere. But the size is not the only indicator. The quality of the qubit is very, very important. As I said before, qubits are very sensitive to noise. So if there's a very small fluctuation in the environment, the quantum information will collapse and you won't have any good result of your computation. So an important focus needs to be put in terms of this quality. And we need the concept that is directly linked to this quality is something that is called coherence. Coherence is the lifetime of the quantum information before the noise destroys it. Other important factors are connectivity in the chip, interactions between qubits. This is related to the complexity of the problems we can encode, as well as the speed ups that the computation can provide. And another final important milestone is to look at quantum advantage proofs that go beyond artificial proofs of principle. So I say before that this quantum supremacy paper and these quantum advantage proofs have already been there for artificial applications. Now it is important to look at quantum advantage for practical application and something that we call practical quantum advantage.
So you just talked about qubits. And I read a couple of weeks ago that IBM has come out with a computer called, I think, IBM Eagle, which has 127 qubits. And for me, coming from the classical words, 127 bits is like nothing today. So how is it with quantum computers? Is 127 qubits already a size where you would say that that's something that you can use in a practical application, or is it still a research thing? How would you estimate this, or what would you say?
Yeah, exactly. 127 qubits it's a huge feat. So it's a great milestone that has been overcome by IBM.
Okay.
And the magic of quantum computing and qubits is that instead of having 127 bits, now you have 2 to the n bits. So while you are doing the quantum computation, you can actually access the 2 to the n different combinations of zeros and ones that would be your bits. So this can be seen as a massively parallel opportunity to do the computation. So 127 qubits is at the end of the day 2 to the 127 bits.
So it's a huge, much more than 127 bits, right? So you can put much more information into 127 qubits than you can put into 127 bits. Is that the message?
Yeah, exactly. Okay. So it allows you to investigate a much what space inside your computation, and that's the key thing of qubits and quantum information.
What I'm asking myself all the time, I'm reading about quantum computing, is something like when I compare it to classical computing, I have an understanding of, okay, it started in 1940s and then came the 50s and the 60s with the development of the transistor and stuff like that. When you compare this, where are we now? Are we in the 1960s of quantum computing, or in the 1970s, 1980s, or are we already in the today? You know what I mean? So the comparison of the time scale of the development of the classical computer versus the quantum computer.
Yeah, absolutely. So I wouldn't say that we are at the same level of classical computation. So classical computation at the end of the day has had a huge evolution, a tremendous evolution. So it's great where it is. And quantum computing is just at its infancy. So very, very, very beginning of this technological revolution that we expect to see with quantum computing, similar to what happens with classical computers. But I would say that we are still in a very early stage.
That's what would be my observation too. But when you compare it to classical computers, back in the 1950s and 1960s, were also banks who started using these early processors and computers. Also, they were quite immature. They started using it. So I understand that banks right now start trying to figure out what they can do with quantum computers. Also, they are still quite young and in early stages, because the benefit might be huge, right? And you talked about the fields of applications, like optimization problems that we have, like in risk controlling or in capital markets, simulation things. I think it's justified that banks are thinking about quantum computers, right?
Yeah, absolutely. I think now it's a exploration stage where, as I said before, I think it's a good idea that these financial institutions start trying to understand, to get educated on what quantum can do for them, and start maybe doing the first moves on translating their problems into quantum algorithms. You already have available some quantum computing prototypes that you can use to run very small algorithms. So you can start doing some experiments with real devices and see how this yields the result and how this can be beneficial for you. So I think it's time now to start exploring all these possibilities.
Speaking of possibilities, you mentioned earlier a couple of areas where this could be interesting. And in our topic group, Advanced Intelligence at ZDB, we, as the name suggests, also look at artificial intelligence, which is often computational, very intensive. So apart from just the efficiency gain there, do you think there will be an effect on the field of artificial intelligence, machine learning? Will it boost the development, or what are your predictions for this area? What will we see there?
Yeah, absolutely. So as I said before, quantum computers are not ready yet to overcome the classical information technologies that we see now. So I think we are going to see some hybrid approach where the quantum computer is some sort of accelerator of the classical one, and all the different models of computation coexist together. So for instance, now with the example of artificial intelligence and machine learning and all data science and so on, we are already seeing a lot of hybrid techniques that combine the quantum processing with machine learning. And there are many focuses in research that are trying to understand how a quantum processing unit, what would be a QPU, which is the processing unit of a quantum computer, could harness huge amounts of data and using different machine learning ideas that are coming from the classical computer science field. This quantum processing unit could benefit. So you could take the most of the quantum part and the most of machine learning and combine them together to very powerful algorithms to deal with big amounts of data.
So would you say that in the future I could have a QPU together with the CPU and the GPU in my notebook? Is that a scenario?
Well, I don't know if that's going to translate into personal computers, because quantum computers at the moment are very bulky and very big and quite expensive to build. So at the moment, the quantum computers are something that seems to be more suitable for the cloud. So you connect through an online cloud service to the quantum computer, that it's located in a lab with all the equipment necessary, and you do the computations through the internet. So this is very similar to what happens with the high-performance computers, with these supercomputing centers that are located in a dedicated place, and you just send your calculation there, and the result comes back. So what I imagine exactly what you say is that we will have CPUs, GPUs, and other components, and on top of that, QPUs. And the QPU, so the quantum processing unit, will be used as an accelerator that will take some specific computation, some parts of the computation, and do it in a very faster way than what the CPU or GPU would. And then you run everything in the supercomputing or in the high-performance computing facility, and you get back your result. So because of that, it's really important to create good access stacks in terms of software that allow you to codify your problem from your home, from your laptop, into a quantum algorithm that then goes to this supercomputing facility and separates what goes to CPU, GPU, QPU in an efficient manner.
So there's a famous quote, I think it's from Thomas Watson, the then president of IBM, who said, I think there is a world market for maybe 5 computers. He said it back in the 1940s, I think. Do you think that the same applies for quantum computers as well? So will be there a monopoly of very few manufacturers and very few providers of those computers because they are still so expensive to build, so expensive to run, or will there be some scale and there might be a huge market for it?
Well, this goes very much in line with the problem. For one of the challenge that we have at the moment, and is that the quantum computing, the understanding of quantum computers and everything that surrounds them is only for a few, because you need to have a very specialized education to be able to program them, to design them, and so on. But as we develop the basic research lines of them, and as this becomes more of a widespread technology, we are going to end up seeing something similar to what happens with classical computers, with the laptops. So now you can have high school students that program with their laptop, and maybe they didn't have to go through a PhD in computer science I expect something similar to happen.
Yes, of course.
But this takes time, of course.
So you mentioned essentially a couple of kind of issues that still need to be overcome. One is essentially the size, and also related to this, kind of the cost of maintaining it and also working on it, but also now the kind of lack of democratization of it. What do you think are, apart from these things, that the technology needs to overcome in order for it to become mainstream or have a chance at becoming mainstream?
Yeah, so as I mentioned before, and as you just recall, there's few main challenges to overcome from the technical side. So we need to enlarge the size of the chips. We need more qubits, but we are going in the right direction. So as we said before, IBM is doing quite large chips. Google is also on the same roadmap, and many new companies, startups in Europe, in the US, and so on are also tackling into that direction. The other challenge is quality. As I said before, we need better qualities for our qubits. We need larger coherence times in order to have larger computations. Otherwise, we can only tackle very small computations that would probably have a classical solution that is efficient. So in order to have a practical quantum advantage, in order to find some speed ups of quantum computers, we need to be able to run them for large problems. And that means running them for larger amounts of time. One of the other challenge or milestones to overcome is the problematic that we encounter with the lack of experts that there are in the field. So we have a problem with human resources. So many companies are appearing, many research groups, but not so many people available to hire, and that's a big issue. So it's important to, as I said before, provide good training programs, promote the different education programs at university that focus on quantum technologies, not only on quantum computing, but also some of the causes of quantum sensing, quantum communication, and so on. It's important to promote these programs. And also give good consultancy services, provide cloud access to the devices, like have open source algorithms that people can start try in the different available devices that you can access on the cloud, such that people can start learning how to use this new technology. Otherwise, we will have the issue that we were talking before, that this is going to only be for experts. And if we want this to have a widespread impact in industry and in practical applications, we need to make this technology available to everyone.
Are there places where I can go today to learn, to work, or to program quantum computers? Or are there books or schools? You know of some?
Yeah, I know there are plenty of these online training programs that are quite start from scratch, and they are provided by MIT and different universities. I'm talking about these online education short courses. There's also a lot of training programs that are mainly provided by IBM. IBM is putting a lot of focus on these training programs using their software stack, what they call Qiskit. And there are many different events on hackathons and conferences that aim to provide a very top-down approach of how to program quantum algorithms with their machines. And those are very useful to learn the basics of quantum computing.
So I could start today, right? So after this,
yeah, absolutely.
I could go to IBM and watch one of their videos and start programming. That sounds great.
Yeah, and you can actually have access to their machines. So some of them are open, and so you can use them. I think they have different devices with 5 qubits that you can access to and run a small algorithm. Of course, it's not going to be a big algorithm because with 5 qubits you don't have that much to do, but it's great for experiments.
Yeah, as you said, gaining experience is important now, right? It's a very new technology, but very promising.
Yeah, absolutely.
Yeah, thank you so much, Marta, for all of these insights into the world of quantum computing, and especially for your perspective on what it might mean for financial services institutions.
Thank you very much for having me here. It was a pleasure.
And also thanks to Matthias for joining me. Yeah, thank you. It was a pleasure for me too. It was very insightful, and I gained some really helpful experience and on quantum computing. Thank you very much. That's all for this installment of Sound of Finance, a podcast series by ZDB. You can find further discussions on this and other interesting topics regarding the world of finance on our website, zeb.consulting.com. Also, if you haven't already, be sure to subscribe to this podcast via your favorite platform. We hope you enjoyed today's conversation and that we will talk to you in the next one.